Greetings everyone. Here's a short video about Project 2 in our course M570, Calculus for Teachers. So the first thing you need to know is where can I find a statement of the project? And of course that's in week 4 at the bottom of the page. If I scroll down here to the bottom, you'll see a PDF that states the project. Here it is, Project 2, downloading. I'll open it up, pull it into my window here, and take a quick look at it. My little preamble says most of the differential calculus seems to be pointed at the algebraic rules for finding derivatives of known functions. But this is really not realistic. Rarely do we look at the world from easily know the function that relates to variables. More commonly, what we do is gather data and attempt to model a function that best fits the data before applying the tools of calculus. So that's what I want you to experience in this second half of our project. And so I want you to be able to find or have some experience trying to find a reasonable algebraic representation that is a function for a real-world data set, and then find its first and second derivatives using an algebraic approach, so that informs your understanding of how one quantity changes with respect to another. So in terms of differentiation, just think about this. If your knowledge of calculus is strong, or you consider yourself a strong calculus knower, then carry out 2 analyses. If your knowledge of calculus is still developing, then just carry out 1. And if you're even stronger, then I'd encourage you to find your own data and try to carry out similar analysis on data sets that you find for yourself. So the data sets that we'll use, the sort of stock data sets, are the same ones from before. I saw in the first project people do world population, the rectangular volumes, and the Missoula day lengths data. And so I would expect that you would probably use the same data that you did before just because you're familiar with it, but I'm not restricting you to that. If you want to do a different one, that's certainly up to you. Go for it if you want to try, say, a variation. So what's the project requirements? What I'd ask you to first is to explore finding a function that best fits the data. I purposely chose data that I thought could be modeled by some of the functions that we've seen in the course. So hopefully that gives you some idea of, each one of these you should be able to model somehow using either a polynomial function, which we looked at those. We know how to find derivatives of polynomials. A exponential or logarithmic function, we know how to handle those, and we also know how to do periodic functions, so things like sine and cosine. So that is the idea. So here we go. I say the words best and fits are in quotations in the previous sentence because this instruction is highly subjective and debated among mathematicians. I mean, how do we know when something fits best? So I really leave it up to you to choose what you think is best, and I just encourage you to use technology to explore how different functions can be fit to the data before you choose one. And like I said, I'll model this procedure in a video, and I'm doing that right now. So once you have a best fit function, then would you display both a graphical, create a graphical display of the best fit function over the top of the data. You can use technology to carry this out. Desmos or GeoGebra or Excel works great to do this. And then go ahead and use what we've learned in the course. That is, we have these rules of differentiation. We have a whole new, what we would think of a whole new algebra to find the first and second derivatives. So in this case, you're not going to be looking for a first and second derivative graph of data. You're going to just be looking for a first and second derivative as an algebraic function. And then go ahead and create graphical displays of this first and second derivatives. If you want, if you're so inclined, you could put those over the data that you did in Project 1 that's supposed to be the data of the first and second derivatives. So that'd be interesting, but not required. And then a short report that identifies at least 3 findings that can be concluded from the algebraic or graphical representations of the first and second derivatives. So something you discovered by, I guess, calculating first and second derivatives. Okay, so let's go ahead and take a look at an example. Okay, so here is my bikes project, the example project I did for project 1, and as you recall, it sort of has the years and the number of bikes in the millions. I did most of my graphs in Excel, so you can see kind of my graphs for my example project here for first and second derivatives, as well as, the actual, I guess, number of bikes produced. But what we're going to try to do is we're going to try to sort of find a function that passes through this data. So what I'm going to do is I'm going to go ahead and copy this. And once I copy it, I can go over into Desmos, and I'm going to just go ahead and dump it in there. And there it is. It looks like that. And my hope is that I can find some sort of a function that that models this data. So there's a few things that I could do right now. I could adjust the x-intercept, or I should say the x values, such that 0 would be 1950. The reason I might think to do that is because these are fairly large numbers. It might simplify the function quite a bit if I just if I adjusted that. So I think I'm going to go ahead and do that. I'm going to make this 0, then this would be 10. Oops. Undo. Let's see. And this one would be 20, and this one would be 30, and this one would be 40, and this one would be 50, and this one would be 60. So 60 years of data. Of course, that adjusts the graph quite a bit. We get something that looks more like this, and has, I guess, a starting y-intercept of 11. It looks like. So that's just one way. I don't know if you'll want to do that or not. Oftentimes we do that with time series data. If year is the x value, I guess the reason is it just simplifies the model that we're creating. We're using kind of smaller numbers, so we would expect easier numbers in the model that we create. So now the question is how can we get the computer to find a model here? So in Desmos, I don't know if you've ever done this, but Desmos has a really nice way of finding models. And so, for example, one model we might all be familiar with is y equals mx plus b. So, y equals mx plus b. If you put that in, what it's going to do is it's going to say, well, do you want a slider here? And of course, you could do a slider. And so sliders are sort of these, well, just what they sound like, a slider. And you could adjust the slope here, and you could adjust the y-intercept to get to where you think you have a pretty good linear model, and that could be your linear model for the data. But I kind of noticed that there's this sort of dip below and then a dip above, and my subjective, I guess, analysis says that this linear model is perhaps not the best model. To me, it seems like it accelerated here and then it decelerated across the later years. And in fact, bicycle production is slowing a lot in the last few years. So I'm going to kind of reject the linear model, and I'll sort of think to myself that I want something that's has more curves in it, and so polynomials come to mind. Polynomials are these curvy functions that that can be used to fit more curvy things, and in particular, they're not like an exponential model that just curves up constantly. They have twists in them. So this idea of concave up, concave down, we see that often with polynomial models. So I'm going to try to find a polynomial model. So one way you could do that is you could hand fit it. You could say, well, I want something ax squared, plus bx plus c, and it says, do you want sliders? Also go ahead and add a slider. So then I can go ahead and get rid of m here. I've got a, b, and c, and I can model this, using a. Well, it looks like it needs to be really wide, but concave up. I don't know, c could be moved along here. I don't know, c is the x-intercept, so I guess I would take it up to there and then maybe adjust my a value. It gets really sensitive there, so one thing you can do is you can say, well, I'm definitely between 0 and 1, so I'll put a 0 here and maybe a 1 here and let the step size be 0, 1. So then I get a much finer slider that I could sort of adjust out like this. And I can see that, well, I can get something that, sort of I guess works pretty good for the first 4 or 5 points, but then those last 2 points are definitely out. I mean, it feels like it's not a realistic model because there's no chance for a deceleration on the 40th year from I guess 1990 on. So I don't really like that model as well. But I guess what I'm showing you is a method for hand fitting models, which is perfectly fine. If you prefer to hand fit, I would encourage you to just type in the equation of the model you're trying to get, whether that's an exponential model or a sine model, and put these little parameters in where you think you might need them. And then just play around with it, see if you can get it to fit. There is an easier way, if you're, well, maybe not an easier way, but there is another way. So I'm going to show you the other way. So the other way to do this is to use Desmos's pre-built regression, and the difference here is that you have to reference data. So I'm going to have to reference x1, y sub 1, and I have to use a tilde instead of an equal sign. So let me show you how this changes. So I'll do a tilde here, and the tilde is, on my keyboard is above tab, so it's that little symbol. And then I need a y sub 1 and an x sub 1 in every one. So what this is really saying is relate y sub 1 to x sub 1 using the model ax squared plus bx plus c. And you can see what happens is you get this model. I'm going to go ahead and get rid of these guys. And well, there's I guess the best fit quadratic according to Desmos. And just some things, you get some statistics here. The statistics are the R squared value, which is the correlation coefficient. The closer this number is to 1, typically the better the fit is in terms of the model passing through the points. And then you also get this thing called residuals, that's just the distance between each one of the data points and the function. And you can actually plot those if you want to. So this little red line here shows that, or red dot shows that this green dot is that far below the function. So you can see this residual is negative, this residual is negative, this residual is positive. It's about 10 units or above, I guess, the function, and so on. Sometimes people like to plot residuals because what you're looking for in residuals is no discernible pattern, meaning that the randomness is all that's left over. But here I definitely see a discernible pattern of down, up, and down, so meaning that perhaps there's a different function that fits it better if I can see a pattern in the residuals, meaning we haven't captured all the pattern by using the function to approximate the data. Hope that makes sense. You can always turn those residuals off to right here, so you can turn them off in Desmos's data table too. Okay, well, so suppose I don't like that function. What if I tried a cubic? So what that would mean is just adding another value to the function that's cubic. So I've used a, b, and c. I'll put a d here times x sub 1, and I'll raise that to the third power, and I'll add it to the cubic. And now I'm starting to see something that looks a little bit better. It incidentally has a higher R squared value as well, and it's showing sort of an increase and then sort of a deceleration as we get to the top, and then it's predicting, if we believe the functions model in the future, a drop. But if I just look at the region where the data is, and not sort of before and after, I can see that I'm definitely getting some of the behavior I was looking for in the data. That is, that there's sort of this acceleration and then a deceleration, but I do feel like the fit up here is not all that great. That maybe it should accelerate more and then top out and go this way. Again, this is part of the subjective model fitting. Perhaps this is where you will stop and say, this is the model I like. It seems to capture what I want to see as a function that's close to the data points. If we take a quick look at residuals here, you can see that there's definitely the residuals are closer, I guess, to the y-axis, meaning they're smaller in value, but still sort of an up, down, up pattern here that I would like to be able to capture a little bit better. So I'm going to go one more step. I'll turn off my residuals. And let's try a quartic and see how that works. So that's a fourth degree polynomial. So you can't use the letter E. That's reserved for the exponential function in Desmos, so be aware of that. So instead of A, B, C, D, E, I'll put an F in front of this. I'll do Fx sub 1 raised to the fourth power and add that to my cubic and see what that looks like. Okay, so there's the fourth degree polynomial. At first I stopped the video there for a second because I thought Desmos was having a problem, because to me it looked like, for those of you who teach algebra, it looked like a cubic polynomial because the end behavior was, you know, positive infinity on this side and it looked like negative infinity on this side. So I panicked thinking that Desmos wasn't behaving. But then when I zoom out, you see the right end behavior. So in other words, it should be going to positive infinity in both directions if the leading coefficient is positive. So I was a little worried about that at first, but it really looks very similar to the cubic. And I don't know if you noticed this, but the F coefficient, the part that is that the fourth degree the fourth degree, I guess, term in the polynomial is contributing, is very small. It's a very small coefficient in front of there, so meaning that, you know, we get a little bit of change in behavior by adding in a fourth degree term, but not a ton because it's so muted out by the multiplier that's placed in front of it. So kind of interesting. I'm going to go one more and just see if I can do one better with a fifth degree polynomial. See what that has. So EF, let's do G x to the fifth. Oh, and by the way, I gotta be careful. It's got to be x sub 1 to the fifth plus. And that's where I kind of feel like I get a better picture when I did this before in preparation. I think this is the model that I will probably choose. I noticed that the residual, or the r squared value, is really close to 1. When you take a look at the residuals, they're all very close to 0. There's a little bit of up, down, up still left for, I guess, this point, and this point. But the other ones are all very close to 0. So I kind of feel like the fifth degree polynomial fits the data the best. That being said, I don't think I believe the end behavior. I don't believe that things are going to take off that quickly after, I guess, 1910. But I do like the way that it is fitting the data in between here. So I think I'm going to go ahead and keep that as my example of the best, I guess, fit polynomial for the data, at least in terms of fitting the data in the time frame in which the data exists. If I was to sort of say, try to predict what's going to happen in the future, I might go back to the fourth degree polynomial, because I kind of feel like the fourth degree polynomial showed things sort of tapering off and perhaps turning negative. But who knows what the future brings, right? This idea of extrapolation, or taking, finding a model that fits the data and then using it to predict the future, is really controversial in math. Because of course we don't know what the future is going to bring, and it's hard to say exactly what the behavior will be. But that being said, I don't believe that this will be the behavior, but who knows, maybe it might be. Anyway, so this would be the model that I would probably use. So I would copy down the 1, 2, 3, 4, 5, 6 parameters of my model, and they are these right here, and make that into my polynomial model, which I could then find a derivative of pretty easily, and I could find a second derivative of as well. So what'll be interesting is we'll be able to to plot those. You can do that, for example, in Desmos by just creating a function. And now that the G, F, and all of these have been I guess, created as values in the model, I can go ahead and plot them without the x sub 1s. Does this make sense? I hope it does. So I'll take away the x sub 1s here, and we'll just plot the function. Oh, I just erased it, sorry. F of x, I'll just do it, g x raised to the fifth. Well, I just caught myself making a mistake there, sorry. So if you type in f of x here, which is what I was doing, it what will happen is it'll make this function no longer available, or the model no longer available. It says f is a function, try using parentheses. So what I discovered is that I can't call this f. I have to call this something else like h if I want to use the values from the function above. Otherwise it overwrites f and erases all the parameters that are stored above. So I'll do h is equal to g times x raised to the fifth. Okay, well there's gx to the fifth plus, let's see, fx raised to the fourth plus dx raised to the third plus ax raised to the second plus bx plus c. And there it is. Now I have that thing written in. I can take the red function out. I can maybe get rid of these. And we have a good picture, I guess, of the model that I would use to model the bike sales across the, I guess, the latter part of the 20th century and into the first 10 years of the 21st century. But what's kind of neat here is that we can then take a look at what the derivative looks like. So we can call h, I don't know, let's call it I of x is equal to d by dx of h of x. And so there's a picture of the derivative function. And so that could be your first derivative, and then j of x could be equal to the second derivative, so that'll be just d by dx of I of x. And we get a sense of these two functions and what they look like. Of course, not a very nice picture, but one thing I think that's kind of neat is that you can then find out, you know, what the maximum is, for example, and what the minimums are for the first derivative. So what's kind of interesting to me is about 29 years after 1950, so I guess that's 1979, we have the very steepest slope, the steepest first derivative, and it's 3.155. So in the context of my data, that means that in year 29.2, so I guess, you know, just at the first part of 1979, bike sales were the highest, were increasing, I guess, at the fastest rate in over the historical period, and they were increasing by about, I believe it's 3.155 million per year. So in other words, the slope of the graph at this point right here, 1979.2, is the highest among all slopes. So that's kind of interesting. Right there is the rate at which, I guess, the bicycle manufacturing was increasing. So that must have been like the most promising period in history, I guess, in terms of the growth in the industry. And then we see things really taper off. You know, I guess here, I don't quite know if I believe it, but you know, there's a low point here. I'm just holding my left mouse button over the function, and you can get a traceable point, and it'll snap at low levels. So that's a low value of slope. You can see that it's a relative minimum on the first derivative. So a low value of the slope there, and then there's also a very low value of the slope here at 51. So I guess that would be 2001. We saw the rate slow to just 234,000 bicycles per year. Still increasing, of course, but increasing at a rate that's much lower than it was back here. So that seems to be reflected in the graph. You know, we have a high, you know, high slope graph here, but by the time we get to here, we're a pretty low sloped graph as well. So some things that you could discover from the first derivative. The second derivative, I think, is fun to think about too. It's going to be harder to see in this scale because we're so compressed. So what I'd probably do is increase my y-axis or decrease my y-axis to get a good look at it. So I'd probably just go to 2 from 0. Okay, so here's the second derivative right here, and it's saying that it's positively valued, so concave up roughly in this period. So from 1957 to 1979, so nice and concave up in that. So I guess what we can say is that bicycle manufacturing is accelerating across that interval. But then the value here where it crosses in 1979 again turns out to be an inflection point. That's interesting. It's both an inflection point and right, a maximum first derivative. So I guess what that means is that in 1979 we saw the rate of change go from increasing year to year to starting to decrease year to year. Although it's still positive, the rate of change is decreasing. So 1979 seems like it's a really important year in bike manufacturing. That's something I probably mentioned. So there it is. I guess that's roughly what I wanted to show you. I hope that gives you a sense of what I'm looking for. I'm looking for graphs of first and second derivatives based on a model here of a graph of functions. So the model would be, of course, the model that I showed earlier, where I guess this would be about to 110. There it is. So a model that fits the data pretty good. What is its first derivative and second derivative when calculated on that model tell us about the behavior of the data? And I'll go ahead and write up a model project based on what I've discovered in this video. So you'll see graphs of the first and second derivatives, as well as a graph of the function that models the data. And I'll put some of the observations I made in this video into words, and hopefully that'll give you a good sense of what I'm looking for in your analysis for Project 2. Once again, and as always, if you have questions, just go ahead and reach out to me via email, and I'd be happy to answer them. And I look forward to seeing what you get. All right, good luck.